And I would like to introduce Bill Nelson. He will be presenting Basics of Quantum Computing and the Threat to Asymmetric Encryption. This is his first time presenting NANOG, and it's a pleasure to have you on board. Welcome, Bill. Thank you.
Thank you. Let's see. Good afternoon, and thank you for being here. You didn't have to be here, so I appreciate it. My name is Bill Nelson, and I'm a longtime NANOG lurker. This is my first time presenting. I've learned a lot from our community over the decades, so it's nice to stand up here and try to give a little bit back. This is what we're going to discuss in the next 25 minutes. We're going to talk about the problem with quantum computers, how quantum mechanics and computers work, tracking the state of the art of a quantum computer, the state of the art, timelines until one gets here, and what can be done about it before one does get here. Now, I'm going to use the terms quantum computer, quantum processor, and QPU interchangeably throughout. They mean the same thing. I have given a version of this presentation 2 previous times, and each time the question portion drove us well over an hour, and if I stay on script, we'll have 5 minutes. So if we need to, we can just continue this out in the hallway, and tomorrow, if we want to continue it further, I'm going to wear a bright orange shirt just to be easy to find. Let's have a chat if you want to. I also wanted this deck to be able to stand on its own as much as possible without a presenter, so some of the slides are wordy. I apologize for that, but I did my best to try to slim them down. By the end of this, I want you to be able to track at a coarse but meaningful level the state of the art of quantum computing to a real number that represents a real threat. This is going to be a lot of new information in a little amount of time, so let's get going. This is who I am, the 7 bullet points. I have the general skill set that would imply. I've had a good luck to become a jack of a lot of trades and even a specialist of a few. But I need to tell you exactly what I'm not. Sorry, I got to get used to this is what I'm actually pushing. This is what I'm not. I am not a quantum anything. How I got here to this presentation, besides wanting to give back, is in a call last year, our CTO stated that one of our 2025 goals was investigating the quantum computing threat to the encryption we use at our bank, which happens to be the same encryption that we all use. I used that as justification to go to NANOG 93 in Atlanta, where I attended a presentation titled The Road Towards a Quantum Internet, put on by Melchior Ailmans from Quantum Bridge. And it gave me an introduction to the subject and some paths and questions to pursue. From there, I did a lot of reading and watching of other presentations to get a grip on the subject so I could report back to my company what the threat meant to us. I put together a slide deck to present my analysis with an outline of a high-level mitigation plan by management, and it went well. I had a chance to nerd it up to give to the Cleveland section of the IEEE, and that went well. So I combined them, and we're here today to talk about them. I hope that this will be useful to others. So why even build these things? It's because in the early 1980s, when quantum computers started to become a thing that people were talking about, it was hardware limitations, and that hasn't changed. Today, the largest quantum system simulated in a classical high-performance computing environment is 4 molecules interacting, and it took 16 terabytes of RAM to do it. Hardware limitations are still a very real thing, but in 1994, everything kind of changed, and I'll talk about that in just a second. I do want to mention here early on that a quantum computer is not expected to replace in any way CPUs or GPUs or TPUs. It's like a GPU and a TPU in that it does very specific math very well, but that's it. It's never expected to be in your pocket, and really the only thing it'll do is augment current high-performance computing environments. The next slide is the problem statement, and it is worthy, but it's why we're here, so it's kind of important, and I'll give you all the chance to read through it. Can everyone see that okay? Read it okay? Okay. Thanks, guys. Okay, so to give a name to the math, the discrete logarithm problem underpins the security of Diffie-Hellman, and factoring large numbers into their component primes underpins the security of RSA. So quantum computers of a certain size will break asymmetric encryption. As far as symmetric encryption goes, a quantum computer weakens it. And that's because in 1995, Dr. Love Grover discovered a quantum algorithm for unstructured database search, which is a fancy way to say brute force attack. The quantum algorithm gives a quadratic speedup over our classical methods, so it is only weakened, it isn't broken. The effect of this weakening and the mitigation methods is an active area of discussion. The rule of thumb so far is that the quantum computer will weaken symmetrical encryption by half, and the solution is to just double your key size to stay quantum resistant. The rest of this presentation will only talk about the asymmetric encryption effects. So these are the main quantum mechanics concepts that we'll cover. I'll throw in some repetition throughout the slides to help remember the new information. And of these, the 3 bolded items are the key concepts in understanding quantum computing. It should be just accepted that it's weird at the quantum scale. Particles can be in different places or states at the same time. They can interfere with themselves, and they can tunnel through energy barriers that they should not. And it's really a bizarre kind of place. It is also completely random, but it follows the rules of probability. Wave-particle duality, quantum mechanics governs the very small, where particles can also be described as waves. The wave function and the state vectors describe the quantum systems mathematically, and I promise I've done my best to do no math in this presentation, or as little math as possible. Measurement collapse is when the act of measuring a quantum system causes it to lose all of its quantumness, and the system becomes a single state. Superposition is where a particle can be in multiple places or states at the same time. Interference of waves is how we'll get answers out of the quantum computers. And entanglement is what gives the quantum computer its massive parallel power. Now, I don't know if anyone can read the real small footnote, but what it says is that this image is of the Lorentz attractor, and it has nothing to do with quantum mechanics. Entanglement has no analog in the classical world of physics, so I thought it was just a surreal visual to try to help imagine what entanglement might be. You'll see that image of the attractor on any slide where we discuss entanglement between particles. So, quantum mechanics governs the very small, and the devil is always in the details of the environment, but for us, we're going to consider 10 nanometers or smaller to be quantum scale. At that scale, a particle is not just a particle, but it also behaves like and can be described as a wave. As an example of superposition, say we have a two-state quantum system like electron spin, where it can be electron spin up or electron spin down. Until we measure the electron spin, it is in a superposition of both states at the same time, of being spin up and spin down. As soon as we measure the electron spin, the electron will become only spin up or only spin down, and that's called measurement collapse. When a quantum system is measured, the superposition of probabilistic states that the system was in becomes just a single definite state. Again, this is called the measurement collapse, when we lose all that quantumness of the system. So, interference is a multi-wave interaction where the combination of the waves makes one composite wave. And creative manipulation of these probability waves via quantum algorithms to get different wave interference patterns is how a quantum computer gets to its answer. I don't know how well anyone can see it, but that is a red line that's supposed to represent the composite wave of green and blue waves. Sorry to anybody that's colorblind, that was a horrible choice. So entanglement, this is the very, very weird one. When two quantum particles are entangled, the state of one particle cannot be described without describing the state of the other. Because they describe each other, any changes to one particle of an entangled set of particles are instantly correlated across the entire set, regardless of the distance between the particles. And this is what Einstein famously called spooky action at a distance. The no-cloning theorem states that it's impossible to create an exact copy of a quantum system that is in an unknown quantum state. This comes into play for quantum networking as well as quantum computing error correction. A qubit, the base unit of quantum information, cannot be regenerated like a normal classical long-distance signal can be. So as far as the qubit can be coherently sent in a single shot is as wide as your quantum network will ever be. The other part is with error correction. So classical error correction can replicate bits and place them all over and use some creative methods to detect and correct these errors. Because of the theorem, you can't do that with a qubit, and so error correction becomes incredibly difficult. So the qubit is the fundamental unit of quantum information as analogous to a bit in a normal computer. For two-state quantum systems that we can use, examples are electron spin, we can use nuclear spin, we can use photon polarization. Superconducting qubits have current that goes clockwise and counterclockwise at the same time. Like an atomic clock, we could use two hyperfine atomic ground states. There's a number of physical modalities for a qubit. I do want to explain why I emphasized certain calculations. The quantum computer only excels when the math in the algorithm makes use of superposition and entanglement. If it doesn't make use of superposition and entanglement, it's not a quantum algorithm. You can just run it on classical hardware. So all qubit modalities are noisy, and so to try and eliminate noise, quantum computers are extremely isolated and extremely cold. They are around millikelvins above absolute zero. But even just sitting there, the qubit's errors will trend to infinity, or what's called the state of decoherence. So really, a physical qubit is capable of taking in quality data and returning garbage. So you might ask, what's the point? In comes the logical qubit. A logical qubit is also called an error-corrected qubit, which is a misnomer. It's not error-corrected, it's error-mitigated. It still trends to infinity. And today, by far, quantum error correction is the #1 research area in quantum computing. So we can work longer with a logical qubit, but the state of decoherence, while delayed, is still inevitable. Oh, I didn't get that. Oh, sorry. This is the logical qubit slide. I'll get it by the end, I promise. Okay, the entangled qubit. This is why a quantum computer is so powerful. As you scan the slide, I hope you recognize that this is base 2 math from IP addressing and subnetting. Instead of being able to represent one number out of 2 to the n options, though, a quantum computer can represent all 2 to the n options at once. Every time a qubit is entangled in a quantum computer, the state space a quantum computer can adjust at one time gets doubled, kind of like Moore's law. But instead of doubling the number of transistors to double the power, it's just entangling one more qubit to double the power of a quantum processor. Recall that entanglement of qubits means you cannot describe the state of one qubit without describing the state of the other qubits. A calculation on one entangled qubit instantly adjusts the values of all other entangled qubits. That's where quantum parallelism comes from. Now, the record for entangled qubits in a real quantum computer is 24 by Microsoft and Atom Computing. And real quick, subnet mask, that's the same number as hosts in a /8. So you got 16,777,216 states you can manipulate at once. In a simulated quantum computer, the record of entangled qubits is 40. 2 to the 40 is 1.1 trillion states that it could manipulate at any one time. If you use 16 bytes per state, that's where you get 16 terabytes of RAM in order to run your quantum computer, simulate your quantum computer. Anecdotally, interesting things are supposed to happen in quantum chemistry around 100 entangled qubits. And that's what we need to know about qubits. Next is how would we go about adjusting a qubit? And that's the quantum logic gate. Quantum logic gate is the base unit of a quantum algorithm and can alter the probability the qubit will be a 1 or 0, as well as adjust the XYZ orientation of the probability wave. And I think this part's kind of cool. So once a qubit is in place, if it's movable, not all of them are, but it stays in place for the duration of the algorithm. So classically, I've always thought about bits moving through circuits to get to where they're going. But in this case, a quantum computer, we're bringing the circuit to the qubit itself. Like qubit error correction, quantum logic gate error correction is a non-trivial task. And again, error correction is the #1 area of research in quantum computers. So let's run through a quick made-up example to kind of see how a quantum computer massages out its answers. This is an example of a 3-qubit computer that's going to do its thing. The column on the left are the potential answers in the form of a bit string, and the column on the right shows the probability amplitudes that that answer will be measured. The piping greater than symbols around the bit strings is called ket notation, and I don't understand the math well enough to know why they use it, but I heard in another presentation to just think of it as meaning something quantum. We'll initialize all the qubits so they all start out with an equal probability across the 8 possible bit strings. Since quantum computers deal with randomness and probabilities, a quantum algorithm is never run just once, but many, many times in order to get confidence that the returned bit string is correct. The quantum computer will arrive at its answer by running an algorithm that adjusts the interference patterns of the qubits in order to increase the probability of the correct answer being measured through constructive interference and suppressing the incorrect answers through destructive interference. After we run it through a layer of gates, we might end up with a probability amplitude graph that looks like this. Run it through another set, and we're starting to see something come out. And at the end of any clever quantum algorithm, there should be an interference pattern where the qubits probability waves constructively interfere in a way that amplifies the correct answer and destructively interferes in a way that suppresses incorrect answers. In our example, if all things went well, the computer would return the bit string 110, and that means whatever it means on the classical side. And that's how quantum computers work. So let's talk about state of the art. This is what we want to track. It's not much. Don't worry about physical qubits. They're not that important. What's important is the logical qubits. So we're going to track the number of those along with the inflection point of the error rates. Recall from base 2 math that for every logical qubit added to a quantum computer, the potential power of the computer is doubled. Today, with errors trending to infinity, when error correction can actually suppress errors to 0, there's no way to quantify what will happen exactly, but we can expect algorithms to get much more complex and much more interesting very quickly. That image in the corner there is an example of what a quantum circuit diagram looks like for a 4-qubit computer. The gates make up the circuit makes up the algorithm. All right, so here's the number we're going to track to. There's a paper out there that says the minimum number of logical qubits we need to crack an RSA 2048-bit key is 4,098. The paper also states that it will require 608 trillion gate operations on those qubits to accomplish. There's a benchmark out there called quantum volume, invented by IBM, where the record circuit depth today is 25 gate operations. That's it. Here's state of the art, and it is not impressive. The top logical qubit counts are around 100 to 156, 156 being the most. As far as Shor's algorithm goes, I believe it was IBM that successfully factored 15 into 3 and 5, factored 21 into 7 and 3, and failed at factoring 35. So they're a long ways away. Google's Willow on the second indented bullet point there, late last year, was the first successful implementation of logical qubit where the error rate was less than the physical qubits that made it up. And that's the unimpressive state of the art. So what is it that we can do about it? Why now? And the answer is because it takes a long time to swap out encryption. As an example, moving from 3-DES to AES took about 2 decades to accomplish. The other reason is because of an attack called Harvest Now, Decrypt Later. And this is where an adversary collects encrypted data and waits for a cryptographically relevant quantum computer to be developed that can break the encryption. This attack is happening at the nation-state level. We are not nation-states, and it will depend on the data in your environment, but the message is clear from NIST and other countries that the time to get moving on this is now. It's tough to tell management that. You can't invest resources because of a threat, often some fuzzy, uncertain future. And it's even tougher to predict this future timeline because it's a completely brand new paradigm and predicting breakthroughs is just impossible. So we can ask the experts about their opinions. This is a plot of 32 experts on the likelihood a quantum computer will exist that could break an RSA 2048-bit key in 24 hours. And it's within 5, 10, 15, 20, or 30 years. One of the names is Dr. Peter Shor. The rest read like a who's who of research institutions and hyperscalers. What I took from this is that there are a lot of trend lines, but there's also a lot of noise in here. What I told my management is that the NSA has a directive to get all of their entire IT infrastructure to post-quantum resistant encryption by 2035, and I wanted to beat that, and that seemed to get them engaged. This is Dr. Mosca's inequality for determining risk. It's a pretty straightforward way to guesstimate your exposure. X is the amount of time your data needs to be secure and should be known by us, or management, or risk management, or legal if you have those. Y is how long it takes to swap out all your old encryption, and you can estimate that. Whether it's you and a couple subject matter experts, you can get a feel for it. Z then can be messed with just to get a feel of exposure for your data. So from a very, very high level view, we need to find the old encryption, need to replace with new encryption, and we need to document all of it. There is a good chance that this will have to happen again, and you don't want to depend on other people. You want to have resources to refer to. The next slide is another wordy slide. It defines crypto agility, a new concept and a critical capability going forward to remain quantum resistant. So like our problem statement, I'll give you all a chance to read through that as well. So all of the documentation brings this up, and even the big players all have sections on their website that gives their own version of a definition of crypto agility and how to handle it, but it is a new concept that needs to be embraced in order to stay quantum resistant because of the lack of faith in the new algorithms. So what will replace the existing algorithms? These define the new math for quantum resistant asymmetric encryption. And when I say quantum resistant, that also means classically resistant. It's just implied when we're talking about the new algorithms. The algorithm selection process began in 2016 with some 70 submissions and ended in 2024 with 5 standardized algorithms. There are 3 digital signing algorithms and 2 key encapsulation methods. There's 3 types of math being used in the new documents. There is lattice-based, there is code-based, and there is hash-based. And the reason you want to know that is you want to disperse the new algorithms throughout your network in such a way to limit your blast radius should any one algorithm get broken or weakened. It's also useful if you're wanting to mix different types of math to get hybrid keys, which provides an extra layer of security. We also have some RFCs that help us out. RFC 8784 describes an update to IKE version 2. Pre-shared keys are used for authentication only, and this RFC describes updating it so that a pre-shared key is also used in the key derivation function. That will achieve quantum resistance so long as the pre-shared key is sufficiently random. RFC 9242 also updates IKE version 2. It describes fragmenting at the IKE layer instead of the IP layer. The key and signature sizes are all larger with the new algorithms, and fragmentation is, I learned, more efficient to handle at the IKE layer. RFC 9370 describes using multiple key exchange algorithms to establish multiple shared keys that are then mixed to get a single final secret key. The RFC enables the mixing of the new algorithms so that they're based on different types of quantum resistant math, and that way if one of the algorithms gets broken, there is another encryption algorithm holding the fort, so to speak, until the algorithm with broken math gets replaced. This is just a high-level project plan. The most important part is bolded. These are not drop-in replacements for Diffie-Hellman and RSA. They require different compute, they're different key sizes and signature sizes. So the good news is you're going to need a lab, and you could probably justify one for this because you need to stress test this to make sure that your services and applications can stay up using the new algorithms. Let's see, sorry. Okay. So this is just a start of a list of where we're going to look at my company for encryption. We have not begun our task. I do not know if this is enough, but it's a starting point. This will be a brute force project for any of you alive or in the industry for Y2K. It's being called Y2Q Day because of the same brute force mitigation plan that existed back then. This is a listing of all the things you may be able to track about cryptography. I just kind of gathered all the things mentioned in a bunch of articles about what you could track, then I uniqued it and put it in the slide. I have no idea if this is enough or too much or anything, but it's just a good starting point to track or to investigate what you could track about cryptography. And you don't want anything weak getting in. So during vendor management and change management, if you're doing your due diligence on the weakened side of the network, you don't want to let anything else in to screw up your work. So you're going to do your due diligence on vendor and change management. This, unfortunately, don't have time. We need to skip. That is the man himself, Dr. Peter Shore. That's his quantum circuit that is part of the algorithm that will break asymmetric encryption someday. That's it. That's my presentation. Any questions? Okay. Oh.
Hello, Chris Whitfield, currently unaffiliated. I don't think this would probably work for asymmetric encryption, but you might have touched on this. I think you went through something pretty quickly, but for the multiple options for symmetric encryption, would it be viable if you want to, mitigate any threat to one of them to do a consecutive layer through each one? Take the output of one, encrypt with the second, encrypt with the third.
So for symmetric encryption, I have not read anything about that as a mitigation method, so I couldn't speak to it. It's just they've done that with the RFCs for asymmetric.
Okay, thanks.
Thank you. Thanks for being here. Appreciate it.